You should know by now, camera. Camera's like, I'll stop working entirely. Oh shit, sorry.
It really is.
All right, it doesn't want to focus. There we go. It's kind of a fundamental thing I need a camera to do. Okay.
You should get a GoPro.
Now, this is the beginning of the sequence, yes? GoPro. What do you guys notice already that's happening?
That 1/3 is going to cancel out that 1/3.
Yeah, so these
1/4, 1/4.
kill each other.
1/4 and 1/4.
These kill each other.
1/5, 1/5.
These kill each other.
1/6.
Won't this kill with that? Won't this kill with that?
Yeah.
Okay. So what's alive at the beginning of the sequence?
1.5.
1 plus a half, right? Now, what I'm trying to do right now is going to figure out what Sn is. I'm trying to figure out what Sn is. Can somebody remind me what Sn means?
The sum.
Partial sum.
Which partial sum?
Partial sum of the three.
Which one? Is it the first partial sum, the second partial sum? Nth partial sum. So how far do I want to go out in my, so if I wanted the first partial sum, that would be 1 minus, that would be 2/3, yes?
Yep.
The second one would be this. The third one would be this, yes? So I need to go out to what term? Nth term. All right, so let me start down here. All right, so this is let me pull it over here. Dot, dot, dot. Do you see how a bunch of shit cancels in the middle? So let me start at the last number. So the nth term, n equals n. What's it look like? It looks like this, yes? Is that cool?
Yeah.
The nth term, I put an n in, right? What's the term before that one? Now, this is a little weird. All my computer programmers should be wincing a little bit. Or maybe they're okay with that. Let n equal n minus 1. That's a horrible thing, but all right. So what do I get then? If I let n equal n minus 1, this will be
1 over n minus 1 minus 1 over n plus 1.
good. And n equals n minus 2.
1 over n minus 2 minus 1 over n.
Good. And
1 over n minus 3 minus 1 over n minus 1.
all right, let's see what's happening.
Cancels.
You can
All right, let's do one more just to be safe. N minus 4. 1 over n minus 4 minus, John? 1 over n minus 2, right? So see this cancels? Right? See this cancels? Let's see this cancels. So Rico, did I miss anybody? No. Well, let's see. No, I didn't miss anybody. Right, let's do one more. N equals n minus 5. 1 over n minus 5 minus 1 over n minus 3, right? See if this cancels. So see how that's going to cancel with that? At some point you go back far enough, this is answering your question from earlier, how do I know when to stop? When you start to catch, okay, that's going to cancel over here, right? So I don't have to go any further. What's left alive at the end? Yes? So what's Sn? It'll be 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. That's telescoping. Telescoping, of course, means the beginning and the end sort of stays alive, and you just push in the middle disappears. That's why I call it telescoping, yes? Everybody knows telescopes? Yes? And you push it in, so the end and the beginning are still there, and the middle sort of disappears into itself. See how the middle disappeared? All in the middle. All in the middle. Disappeared. And the end is alive, and the beginning is alive. So what's the limit as n goes to infinity of this? Yeah, this goes to 0, and this goes to 0. So it'll be 3 halves. Yes?
The 1/3 never canceled out in the Sn.
Why did I cross through it? Oh, yeah, it did.
This is the rough one.
Oh,
Yeah, that's okay. Thank you, though.
I'm thinking of some words. Okay, sorry.
I think we all, and real quick, do you guys see, that looks like it didn't cancel, but we know it will, don't we? We don't have to keep going. At some point you go, okay, I know the rest of that shit's going to cancel. But you have to go far enough to see who really is left alive. You do the same thing from the end, and the way I do it is I start at the end and then work backwards. until I start to see, okay, there's no reason to keep going. That canceled, so will that, so will anything else before that. You can go far enough until you see what cancels. So look what we just did. We just figured out the nth sum. If I wanted to add, let's check this. Let's check this shit. According to this right here, what would S3 be? Just do this directly. What's S3? It'd be 3/2 minus 1/4, yes? N is 3. Minus 1/5. All right, somebody help me out. What is all that shit? Let's see. 20, 30, 5, 25, 21, 20th? Is that what it is? 21, 20th? Sure. Anybody? Tell me.
Not even here.
I don't know. 3/2. Somebody try to help me out. Times 10, times 5, times 4, so 30 minus 5 minus 4 is 21.
Wait.
Over 20,
Quick math.
right? Yes?
Yeah.
All right,
Yeah. Yeah.
let's do it this way. S3 means the sum of the first 3 elements. That's what S3 means. So we know what any, so now I'm verifying it. Let's do some concrete. So what is 1 minus a third? Holy shit. What's 1/2 minus a fourth? And what's 1/3 minus 1/5?
Yeah.
What?
215.
Yeah!
Oh, you wrote it.
Yeah, I did. All right, I don't know. Hopefully this works. So what's the LCD here? Oh, Jesus. Looks like it's 60, huh? Is that true? 60?
Yeah.
Yeah, that's 60. Okay, so let's see. That'll be 40 60ths plus 15 60ths plus, what is that?
8.
8? There, thank you. Over 60, so that's 55, 63 60ths, which reduces to 21 freaking 20ths. Right, so
Wow.
what we just did is we found a shortcut for the nth partial sum. So if I wanted to know what S314 was, you could either calculate this, calculate this, calculate this, calculate that, calculate that, calculate that, calculate that. All right, I'll stop up to 3, and then add them all together, right? You can do that, totally legit. Right? If you want to do that, you're an interesting case study. I'd much rather use this. So if I want to know what S314 is, it'd be 3/2 minus 1/315 minus 1/316, right? And whatever the shit that is, so somebody could do that for me. I don't know. 4.7, 1.5, it's like 0.8. Is it? No, it can't be that.
Point what? No, it's.
I went way too far. Jeff, 0.00. Okay, 007, 1.5. 1.5. 0.007. Is that right? Oh, screw it. I'm trying to do.
Can someone just give him
I
the?
think it's
Yeah.
1.493.
Yeah.
1.493.
Yeah.
All right, thank you so much. A little faith. All right, I gotta have a little faith in myself. I'm so tired. I don't know how much I could trust. But yeah, okay. Is that? So you can already see S314 is 1.493. This was 1.05, right? So I am getting closer and closer and closer to 1.5, which we know is the answer. I really want everybody. So S sub 1, S sub 2, those are partial sums. How do I figure out the actual sum? One way to do it is to get an expression for Sn, and then let n go to infinity. What would the total sum be? If S5 is the sum of the first 5 elements, what would the actual total sum of this be in symbols, really strange symbols? How far do you want to go to get the whole thing just added up forever? Infinity. If any of you ever write this, but that's what S means. S is the actual sum, letting n go to infinity. So if I can get an expression for the nth partial sum, I stop at the nth term. If I let that go to infinity, if I let n go to infinity, I'm then adding up everything. So we just added an infinite number of numbers, and this looks like a lot of work, but when you say we just added an infinite number of numbers, this is nothing? Are you kidding me? This is nothing. Maybe? I love you guys. All right, let's bring it back. Step here. Let's bring it back. So that's telescoping. You will actually have several telescoping problems in your homework. And I think it's 11.2. Yeah, of course it's 11.2 where they talk about it. Okay. They do an example of telescoping on page 712. Yeah, okay. Kind of had a, yeah, okay, I like it. Yeah, okay. So that's an example of telescoping. It's going to show up a few places. Any? Not you? Yes.
So for n, are we always supposed to go backwards, or can we go forward? For n plus 1, n plus 2?
Well, to be honest, you could kind of start at n minus 5. You got it. The last term is the nth term, right? Because you're going to stop at n. So, I mean, if you want to start, you got to start a little bit back from there if you want to. So, to me, it's just easier to start at the end. The last term will be putting an n in. I know that because what would S5 mean? What would the last term be? Plugging a what in?
A 5.
A 5, right? So Sn means the last thing we want to do is plug it in. So I think it's easier. Now, you don't have to. I think it's easier to start here and then you just start taking a step back and a step back. Because that's how you figure out how far you've got to go back before you can kind of see what's happening. It may be. So telescoping series are nifty. They have all this internal subtraction that's happening, which is what leads us to believe there must be a quick way to do them. And sure enough, you can, for a telescoping series, you can get a nice closed form for the nth partial sum pretty easy. Do you see what I mean by closed form? I mean, it doesn't have like, it's nice and closed, it's nice and quick. Okay.
So for telescoping series, the only way to find that is to actually write out the sequence and find
Yes.
the pattern,
Not the only way, but definitely the easiest way. Right. Once you write out a few elements, you can start to see things cancel, and you get excited. You're like, wait a minute, if I keep going, a lot of shit cancels. That's the whole idea of telescoping series. Is every series telescoping? No, so don't suddenly go, oh, I know how to do every problem. No, you don't. You only know how to do these kind, and they're not all these kind. Yes?
right? So what's like the general form of a telescoping problem? Or how do we know,
Well,
oh, this is telescoping?
The classic thing is it's a fraction minus another fraction, right?
Okay.
That is a very classic telescoping. It could come in different forms. So, if it could be put in that form, then it could be telescoping. Yes, yes, yes.
So if it was like 3 over n minus 3 over n plus 2, you could pull it 3 out, right?
So I'm sorry. Oh, sorry, little dude. If it was what now?
If it was 3 over n minus 3 over n plus 2.
Yeah, then you can pull it beautiful. You just pull a 3 out. The great thing is, watch guys, if this would have had a 4 up here at the beginning, right? I would have pulled a 4 out, and then Sn would have been 4 times that, right? It's just 4 times this. Yes? Yes. I'm sorry.
Do we ever have to view telescopic sums that we get from partial fractions?
Yes, totally. Okay, get out of my brain. I was about to put a problem up that needed, and once you did partial fractions, yeah. Can you imagine it wouldn't start like this? No, you can't imagine that?
Oh, I'm sorry, I was spacing out.
Alright. So it could start as a single ratio, right? In fact, if you put those together, it's n plus 2 minus n, so it'll be 2 over n times n plus 2. You can do partial fractions, break it up, right? So now, knowing partial fractions, so again, if I combine those, if I combine these, is that cool? It'd be n plus 2 minus n over n, so it'd be 2 over n times n plus 2. If you start writing a few sequence elements, it's not going to show you much of anything, because there's no subtraction, right? But if you break this up using partial fractions, you'll get this, which is telescoping. So that was that, and that was a good question. So maybe that'll show up in the homework or the test. You know, maybe. Yes.
If you had like 1 over 2 to the n minus 1 over 3 to the n, could that telescope as well?
All right, let me erase all this. You guys got what you want from this?
Yeah.
More than you want? Okay. All right, so if you think something might be telescoping, so tell me again.
1 over 2 to the n minus 1 over 3 to the n. Oh no, n on the bottom. On that too.
Both the same, but I'll go with you.
Oh, okay.
So, I mean, if you think this might be telescoping, what do you think you do?
Right on top.
Right
Start
on
writing it
top?
out, yeah.
So what do you get? 1/2 minus 1/3, right?
Mhm.
For n equals 1. What would it be for n equals 2?
1 over 4 minus 1 over 9?
Does it look like anything's gonna?
No.
No.
Okay.
Okay.
I got
Not a bad idea. If this would have been 4 to the n, then maybe, right? Because then they kind of go into each other, so maybe they'll be repeated denominators that might cancel. You guys with me?
Mm-hmm.
This one is much better. Can anyone tell me? This is kind of leading into my next thing I wanted to do. Look at each of these by themselves. And I'll do what Robert was saying earlier. I'll break these up. Which you can always do, so it's a good point. You can always break up if that would somehow help you. What kind of series are these?
Geometric?
Yeah, in fact, how many series types do we know at the moment?
2.
Harmonic,
Oh, 3.
geometric,
Arithmetic.
arithmetic, sure.
Oscillatory? Or is that?
Yeah.
That's like
Oscillatory.
category.
Telescoping, right? Okay. So we actually don't know that many yet. But, so in this section when it says, is it convergent, in like section 11.2, you almost definitely want to relate it to a geometric. So I want to do a few examples of what geometric series might look like, because they're not all really easy to tell how to put them together. This one's nice. The first thing I want to do is get a new marker. So, one thing you have to realize is that. Is that cool?
Yeah.
That's a huge thing to realize right now, that those are the same. 1 to the n is 1.
Mm-hmm.
And why is that nice to put it like that? Put it like that, Jeff. There you go. What can you identify very easily now? R. And for a geometric sequence, and again, it doesn't matter if it's like this, to be honest. Just A is the first term,
1/2.
and R is the number that's being raised to an n power.
1/2.
So here, A is 1/2. I love it, because when n is 1, you get 1/2.
Mm-hmm.
And what's R? 1/2. And then what is in this case, if R is, well, let's see, if the absolute value of R is less than, what makes it converge?
1.
That's less than 1. Now, why does that make sense? Because if it equaled 1, it would be the infinite sum of whatever this is. 1/2 times 1 to the n is just sum 1/2 forever. That's going to diverge, right? If you add 1/2 forever, that goes to infinity. Yes? It was greater than 1. Now it's getting bigger each step. So again, that's going to go to infinity. So it's got to be less than 1, so that when it multiplies by itself, it gets smaller and smaller and smaller and smaller. Okay, so what is the sum in this case then?
1/2.
No, I mean,
Oh,
in
for the
general.
Oh,
What's the formula for the sum?
Is it A over 1 minus R?
Kick ass. So over here, what's this guy's sum?
1.
Yeah, we'll say, yeah, it's 1 over 1 minus, 1/2 over 1 minus 1/2,
Mm-hmm.
which is 1 over 2 minus 1, which is 1. And what's this guy's sum?
1/3 over 1
Yeah.
minus 1/3.
Because the first term is 1/3, and the multiple is 1/3,
Mhm.
right?
So that's 1/3.
Let's see, that's 1 over 3 minus 1, so 1/2, right?
Yeah.
So then what's this?
1/2.
1 minus 1/2. 1 minus 1/2. Bam! Yes?
Could
we have done that on the last problem? On like the telescopic one?
No, because
It's not
the
geometric.
bottoms were harmonic. I mean, the series was harmonic, because the bottom was to a first power.
Oh.
Yeah. Okay, so one fact we know, just in case you missed this earlier, one thing we know for sure is the sum of this diverges to infinity. That is a known fact. So if I broke them up, it would have been infinity minus infinity, which, do you guys remember what's true about infinity minus infinity?
It's not a real number.
What form is it in?
Unacceptable.
Indeterminate. Because what matters is who's going to infinity faster, right? The only way this could be some finite number is if they're both going to infinity at the same rate. Do you guys see how it makes sense this is a finite number? Because aren't these sort of going to infinity at the same kind of rate? They're both to the nth power? No? Maybe, okay, maybe. That's why it makes sense that the answer is finite number. Because neither one is growing much faster than the other one. Okay. It's not their sums. All right, yes?
So what if the equation was 1 over 2 to the n plus parentheses negative 1 over 3 to the n?
So, all right, let me make sure I understand. Everybody got this here? Yep.
For that one over there, if it's a over 1 minus r and r is 1/2, shouldn't it be 1 minus 1/2 on the second one?
No, here, r is 1/3.
Oh,
What do I keep multiplying by? 1/3. Can you guys see that?
oh, okay.
Yeah, 1/3 is a repeated multiple, yes. Okay. All right, let me make sure I understand what you're saying. So you're saying if the problem would have started off as, give it to me again.
1 over 2 to the n minus, or plus, parentheses negative 1 over 3 to the n.
Like that, right? Like the negative one's in there also?
Oh, I just meant just the negative one that's in parentheses.
Oh,
So like it would,
wait a
So
minute.
it flips the sign every time.
yeah, so
Like
it would
that?
flip signs. Like,
Oh, yeah, so like this.
yeah.
Okay. Now, the funny thing about that is, so R here is still 1/3, right? In fact, it says absolute value of R has to be less than 1. If that's true, then S is A over 1 minus R, right? So it'd be the same idea, it'd be the same number. This is what we're gonna identify as alternating series later. But let me point out to you, where is it? Bum, 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 bum. Where are you? Here it is. Bum, bum, ba-dum. Where do they do it? Where do they do it? Here it is. I mean, so at the bottom, page 709, they kind of do it. Remember when we did the A plus AR plus AR squared plus AR cubed, and then I multiplied by R, and something, right? Everybody's a little freaked out, but it's very similar to the thing we do with repeating decimals. It's almost the exact same idea. So they do that in a slightly different way, the bottom page 709. I don't know if they give you an example. Yeah, so you can see, as long as the absolute value of R is less than 1, the sum is equal to A over 1 minus R.
So you would just treat it as 1/3?
So here, what's neat is, no, what's R in this case? So this is where I gotta be, it won't be the same answer, let me be a little more careful. Do you see I can rewrite this as this? Is that cool?
Mm-hmm.
What's R then? Here A is 1/2, R is 1/2. Here A is negative 1/3, yes? And what's R?
Negative 1/3.
Negative 1/3. So what's S for this guy? A over 1 minus R. So when you have that alternating thing, R itself would be negative, and that's why it alternates. If I multiply by -2, it becomes negative. By -2, it becomes positive. By -2, it becomes negative. Maybe. So this would have been 4/3, 3/4. Is it negative 1/4?
Yeah.
Neato.
You just, what, didn't you say earlier that R should be 1/3?
Cause it's the absolute value, right?
No, yeah, check to see if it's convergent, right? So to see if it's convergent, the absolute value of R has got to be less than 1. So R is negative 1/3, so the absolute value is 1/3, which is less than 1. Is that cool? But R itself is negative 1/3. Yeah. I like it. I like it.
The thing where you have like a fraction where like they're built to the nth power only works if, and then you take it and just the whole thing is to the nth power, that only works if the numerator is 1, right?
Yes,
Okay.
totally, right? Because 1 equals 1 to the n. Does 2 equal 2 to the n? Nope. Hell no. Only for n equal 1, right? Yeah. But
then
1
you-
equals 1 in the n for all values of n. So I can, wherever I see a 1 in the series, I can just replace it with 1 over n. I can replace it with 1 to the n plus n. I can replace the 1 to the 2n. I can replace it with shit I want. Which is going to become huge later. Okay, you sort of replace it with the thing that makes the most sense at the moment. So for example, if I had I would replace 1 with what? Yeah, 1 to the n plus 7. Right? You guys understand? Okay. Now here A would suck. What would A be? How do you figure out A?
It's gonna be
Plug in
1 to the 4th to the
Plug
8th.
1 in, it'd be 1/4 to the
8th.
8th power.
Shit.
It's a pretty big number.
Or 1 over.
Or pretty small number, I guess.
I think it's.
No way.
No. Oh, screw it, I'm not gonna try.
Yeah, I thought
4 to the 8th in your head.
That's not that hard. Alright, I'm gonna stop. Where's the 8th? Four squared 16 cubed.
64, 256, 1028.
Yeah, you just gotta do 2 enough times.
Yeah.
I didn't want to, I decided it wasn't worth it.
6.
Okay, guys. So, let's do a few things with geometric series. A few more things. Let me take, let's see, take a problem out of the book. I'll trust myself to make one up at the moment. Something interesting, yeah. Oh, real quick. Yeah, why not?
Oh, because it's supposed to be not a fraction.
Let's do this. This is not necessarily geometric. I'm sort of giving it away, it's not geometric.
I didn't think that.
Is this what I want? I think so, yeah. Okay. Don't say anything until I ask for it. But can you guys please put this in what I'm gonna call a closed form? Do you see how this is kind of open? Isn't it open-ended? Does this ever end? No. So when I say closed form, I mean like this. So there's no dot, 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 right? Don't say anything. Can you put it in that form?
Yeah.
All right, do it. Don't say anything. And again, the way you do this is A1, what's the value of n here? N is 1 here. What's the value of n here?
2.
3.
1.
Right, so.
4 times
Sure, Robert.
that. Sorry.
You're fine, you're fine. You guys, now it's out there. What did I do for myself? You're gonna see several problems. I just give you this open-ended plus, 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 right? And what you wanna do is you wanna remind yourself, okay, this is when n is 1, this is when n is 2, and then you start to think, if n is 1, what did I do to 1 to create this? So the top is always freaking 1, that's beautiful, yes? Love when that happens. 1, yay. N is 1, I get 4, n is 2, I get 8, n is 3, I get 12.
4 times n.
Yes, because those are all multiples of 4. I love it. Do you guys see that? You want to tell yourself that's when n is 1, and you want to start to say, what would I have done with n to make this thing show up? Maybe. Now, can anyone tell me if this converges or diverges? Converges or diverges?
It converges.
Is there a constant in there somewhere?
Diverges.
What constant is in here? Good. I'm so happy nobody said 4 that I heard anyway. So kids, take a 1/4 out of the way. And of course, what's left? And what is this?
It converges. I mean, diverges.
diverges.
It diverges. Goes to infinity.
You had a 50-50 chance. No, I know, you know, it diverges, right? Because this is the
Harmonic.
harmonic series.
Yeah.
I like it, and that diverges.
There's too much pressure on.
I like it. Okay, yes?
Can we do a partial fraction problem?
Oh, sure. I'm not even sure if they really, to be honest,
It seems like 11-4.
I don't know if they gave you.
No, they did give us one.
Which
They
one?
did?
It was,
Oh, here we go.
That's fun.
In 43 through 48? Yeah. Okay, here's one.
45. 45 was the part.
Yeah.
But he's not.
It's pretty cool with that? Yes? Okay. Yeah, let's see. Yeah, I'm looking at 48.
For 11.2?
What was it? What was very cute? What is N?
Is that one of the questions you did?
This one's really fun. This one's really fun.
Now I'm really bored.
Let's try and be a 1, by the way. Poor little dude. Okay, here it is. If you just try to, well, actually, is it 1? It's 2, thankfully. Why couldn't this be 1? What happens here?
Because then
1 minus 1.
It's infinity, yeah. So they started as a 2. Makes more sense. So if you try to write out a few sequence elements, you wouldn't really see much going on, right? But when you see something that is rational, where the bottom is a higher degree than the top, well, if the otherwise you would do long division first, right? But when you see something that's fractional with some polynomial stuff going on where it's factorable, attack that sucker with partial fractions, right? So what's the bottom become when you factor it?
1 over n times n squared minus 1.
A lot of That's right. That's right, everybody.
Awesome. Good job, team.
So if I want to look at this, this is not too bad. This is a nice one.
A over n plus b over n minus 1, c over n.
Bless you.
And you gotta multiply them.
Yep, so then you get 1 equals a times n minus 1 n plus 1 plus b times n times plus u plus c times n, yeah, n times n minus 1. Can everybody do that quickly?
Pretty much. For problems like that.
This
yeah.
and n, so when I multiply by this, n's going to cancel, it's going to pick up the other 2 things. So that's going to pick up the other 2 things, that's going to pick up the other 2 things. Bam, 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 bam. Bam, bam, bam. I have this weird feeling that some people don't even know how we got from here to here. Is that true? I just multiply both sides by this, right? Okay. Nothing magic about that. And then now what method do you want to use? Do you want to get like a matrix,
If n equals
system of equations?
You can
Yeah, I'd let n equal,
Negative.
-1 n.
sure, -1. So that would mean that 0, 0, 2c equals 1. C is 1/2. Double check me on that. I think that's right. Yes, Jim, sure. Okay. And if n is 1, we'll get 1 equals 0 plus 2b plus 0, so I get 2b equals 1. B is 1/2. And then if n is 0, because that'll kill 2 things, I'll get negative a. Is that cool? 1 times -1. Negative a equals 1. These guys die, so I get a is -1. So how can I rewrite this series? A, yeah, so -1 over n, yes? Plus
1/2.
1/2, right, so 1 over 2 plus 1 over 2 n plus 1. And then I can start doing my, what do you call it? Writing out the elements, seeing what cancels, right? This is a neat one because it's got 3 parts to it, but stuff will cancel just like before. Is that all right? So just to make sure, I mean, what do you guys start doing now? You start just developing, so what would the first term be?
Negative 1/2.
Negative 1/2 plus
1/2.
2 minus 1 is 1 times 2, so 1/2
1/6.
plus
1/6.
1/6. Shit canceled already, right? That's nice. By the way, is there any way to see that? Yeah, sort of. No, not really. Just plus, and then you just keep going. I'm not gonna, just like we did before, right? You just keep going for a while, and then you have to start at the end and kind of go backwards a bit. It works the exact same way. It's just one more element. So this is what I was saying. It started off like this. You break it up, and it becomes telescoping, or at least you hope it does. I don't know. Let's do one more so that we get negative 1/3 plus, then it's 3. That'll be 1/4 plus 1/8.
None of
That's
that
not
cancels.
encouraging, huh?
None of that cancels.
Aw.
Keep going.
Plus
Keep going.
negative 1/4. Hey, right? Hey, plus. Now n is, so you might want to keep yourself straight like this. There we go. N equals 3, right? So this will be, wait, what did I do? Oh yeah, n equals 2. Thank you, sorry. So I'm not used to when they do it. Okay. 3, 4. Okay, that makes more sense. This would be 1/6. Well, I can buy this sucks. Plus, what is it now? 3, 4, 5, 10, 1/10. Oh gosh. Plus, all right, keep going. At least you got one thing to cancel, right?
So this is not telescopic?
Yay. It might be.
How do we know?
Do you even know?
Start at the end.
Wait, so this is our proof that it's not. So it would be
What do you mean?
divergent?
No, you gotta keep going.
Well, some stuff is.
Again?
We've only done 3 elements.
I'll do one more.
Well, it'll, once you get to n equals 6, it has to cancel.
Yes.
Yeah.
Because then it'll be negative.
Thank you.
How much needs to cancel for it to, well, I guess
The
you need
last
to,
term.
yeah.
You just
Yeah.
need to start seeing the pattern.
Yes.
You gotta keep going.
You gotta keep
Just
going.
gotta keep going.
I love it. I love it. I love it. Yes.
So like, and this is some of the other problems we've done, if you look at the first, like, in this occasion, n equals 2, the last term of n equals 2 is 1/6. And so that's when it starts canceling out, is when you get to the 1/6.
Or when the first guy becomes 1/6, you mean?
Yeah.
Because then that'll cancel
This
there?
is the
Yeah,
last term.
exactly. Okay, I love it. You start to pick up little tells for the problem. Yes.
Doesn't it actually cancel here because the 1/6 combined to 1/3 and then cancels the negative 1/3?
Oh!
That is so fast.
Yeah, you could be doing, what do you say, this 1/6
That
cancels?
1/6 combined to
That's
the positive
super
1/6
cool.
cancels.
Yeah, bam, 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 cool.
Let me see if that happens
And then the
again.
1/4
Nice.
cancel as well.
And so I was looking.
Oh, and then there's
to
2
see-
1/10s.
That's why I was trying to figure out if there was a
Yeah.
quicker.
So we only got 1/4.
way.
No, we
There's
only
a
got
slightly,
1/8.
do you see how this is the only negative
Yeah,
element?
so 1/8 plus 1/10.
Right? So you can actually kind of recombine these.
So all that's left is a 1/8 plus 1/10.
So
For
you
those
have less
3.
stuff to look at in each thing. It's a
I guess
little
not that
bit quicker
much.
then. The only way this could be telescoping is if the negative element cancels some of the positive elements, correct? So you could kind of recombine these if you wanted to. So you got less stuff to look at in each thing. Yeah, you don't have to if you don't want to. Okay.
That's interesting.
Yeah, it might even be a bad idea. When I think about it. Okay, so you gotta go far enough out and see how much actually does cancel. See who's left alive at the beginning, right?
I think once we do the n to the 5th, we'll also cancel the 1/8. Because the 1/4 is already canceled, the next term.
Yeah, right here, the 1/4 cancels. Yeah. Yep. So if you go far enough and you start to realize that stuff cancels here, then you can be pretty confident that stuff's gonna cancel the same way. So it looks like, and this is already, this canceled. That's interesting.
So what are we even missing?
What are you left
Just keep
with?
going.
1/8 and 1/12.
Yeah.
You gotta
Wait,
keep going.
what-
And then you get negative 1/6 and 1/14.
Do a few more terms, right? So this is where you guys, there's something that I like to call math stamina, where you just, I mean, you do like 3 more terms. Is that horrible?
I have 0
No.
math stamina.
Yeah, I know a lot of people have very low stamina, math stamina. Okay. The important thing to realize there is just that partial fractions will show up whenever it wants to. And this is one place where it will show up. In fact, the right way to look at it is we have more tools to do something with this, right? Okay. All right. Yeah, okay, let me find this one more type at least of geometric that I wanted to look at. Yeah, this, well, yeah, that'll work. Yeah, let me make one up, let's see, this could be exciting. It's always exciting when I make some shit up here, let's see.
Oh.
That's gonna be too exciting, let's see. Alright, let's do that, I like it. That's beautiful.
You just started.
Alright, so let me just show you, well, let me see. I want to make this look like this, where A could be 1, or it could end up looking like this. I want it to look like something to an nth power. What's one thing you notice about the 2 powers up there? This one is positive, and this one is. So some of this is going to want to go down, right? Now, what's the extra shit you don't want? I want an nth power, right? Is the best way to kind of look at it. I want to get an nth power. How many extra 4s are there? You guys see what I'm saying? How many extra 4s are there? There's 2 extra 4s. You guys see that? So this is something that we really, really easily forget we can do. 4 to the n plus 2 means 4 to the n times 4 squared. Yes? Because I add powers when I multiply. But that is so easily forgotten or not understood in the first place, right? What can I do with this guy?
5 to the n.
5 to the negative n times
5.
5. You get an extra 5, right? So I get 4 squared times 5. What's 4 squared times 5? 80. And then how do I rewrite this? This, of course, I can put down. And they're both to the n. Is everybody cool with that? 5 to the negative n goes down and becomes 5 to the n, right? Negative power means flip. I'll lock it. So now what have I identified? What's A? 80. What's R? Is this convergent?
Yes.
Could you find what it converges to?
Yes.
Yes. At the beginning, did it look like there was an R? Not really. But you noticed it was constants to an n something power. So you should feel really confident, okay, I can do stuff to this thing to make it look like A times R to the n. And again, it's not that hard and fast. This doesn't have to be n. Right? There doesn't have to be, this could be 1. There's things that could happen. We did one a minute ago where it was n plus 7, if I remember correctly. Right? You just have to know the first term and what you keep multiplying by. That's the only 2 things you need to know. Yes?
Can we factor out a negative 1 from a negative n plus 1?
You could.
I did that and I got a different answer.
No. Okay. So if you do that, you'll get, well, you took out the 4 squared?
Yes.
Yes. You get 16 times 4 to the n times 5 to the negative n minus 1, right?
Yeah, so
Okay.
basically 5 to the power of negative 1 times 5 to the n.
The n is still negative.
So if you pull it down, right, this is negative means flip, and I want to flip these n minus 1 5s. Yes?
Oh.
Yes?
Yeah.
Okay. So this will be 16 times 4 to the n over, and of course the sum should be here and here and here, but screw it. Over 5 to the n times 5 to the negative 1. 5 to the negative 1, flip it. 5 times 16 is 80. You're right back here. So I don't care which way you tear that sucker apart, you're going to end up here. Unless, of course, you do something wrong. You guys start to see how you can manipulate these things? Very often when I see disparate parts with different exponents, can I take some of it off so I make the exponents the same? If you can, do that shit, because then you can combine those things, right? Maybe? Okay, all right. Yes?
I don't know if you've already done this, but can you show why a harmonic series doesn't converge?
So, the book does something that is very unsatisfactory, but page 713. So if you want to see the way the book does it, you can go there.
Okay.
But we're going to show something once we talk about something called the integral test.
Okay.
Yeah. And it'll be much better. Yeah. I don't blame them, because they try to show why before we did the integral test. But I think personally they should have just waited till we did the integral test.
Is the integral test 11.3?
11.3, yes. If I remember correctly. Yeah. Yes.
That's gonna involve like doing improper integrals, right?
Yes. Totally. All right. Which is strange, because we just learned how to do that shit. It's
Yeah.
almost like it's planned or something. Yeah, how do you guys feel? I mean, we hadn't directly talked about this, and this does show up in the homework. And I know what a geometric sequence does. I know when it converges, diverges, and I know even how to find the sum when it converges. I know how to find the sum. That's a lot of shit we know. We just have to know how to take what they give me and put it in a form where I can identify all the stuff I need. I need A, I need R. So can I put it in the right form? Right? Just like putting a line into y equals mx plus b form, right? Same idea. Okay. Just a little harder. All right. Let me think. Let me look at I had an outline of stuff I wanted to talk about. Blah, blah, blah. Oh, that's good. Okay, I love it. How do I show a sequence is decreasing?
A sequence?
That's a derivative.
Yeah, you could. That's one way, but here, show an equals, let me try to not do your homework for you.
I don't know.
What's that, you don't mind?
Limit n
I-
approaches infinity.
Say again?
Limit n approaches infinity.
No,
Oh. Okay.
nope. I want to show that this is decreasing always. Yes?
Do you do it algebraically?
Yeah, yeah.
Do we get,
It just moved it itself.
What's an plus 1? This is the nth term, yes? I want you to realize when we say this, we're actually just designating what the nth term is, and you fill in what n is. You can figure out whatever term you want to, correct? So what's the n plus 1 term?
1 over.
What are you replacing n with?
1 over 2n plus 1.
1 over 2n,
Plus.
Plus 3.
right? Replacing n with n plus 1, correct?
Yeah.
So that is 1 over 2n plus 5. Now tell me, which one of these is bigger?
The one on the left.
Why?
Because it's a bigger number on the bottom.
Wait,
The
which
smaller
one's bigger?
number on the bottom.
Which one's bigger? The one on the left,
The one on the
because
left.
the bottom is
Smaller.
smaller.
Small.
When I divide by less,
Oh.
the result is bigger, right?
Yes.
So that is one where I could just do it. How do I show something's decreasing? I want to show that the next element is less than the one. What am I doing? I want to show that the next element is less than the one before. There you go, Jeff. Love it when you forget what you're doing right in the middle. So, you guys kind of with me? Can you do this all the time? No. No, shit. So, I already heard the magic word just a second ago. Is everybody cool with this? You guys see it? Let this make just immediate sense? A lot of this shit is stuff you don't even realize you're like allowed to do, and it's all kind of new. But I mean, this is directly true. If the next element is always less than the one before, and no matter what n is, isn't this always less than that? Because no matter what n is, this is a smaller bottom. So this is bigger. Is that cool? Is it always that easy to see? No. So let's try one that's not that easy to see. show if decrease or increase or neither. Blah. Okay. This was a nifty one. Ooh, yeah, I love this one.
Is this for 11.3?
No, this is actually 11.1.
Oh.
Yeah. 11.3 has a requirement to show it's decreasing. So if we know how to show increasing or decreasing, we're golden, right? Show us decreasing. By the way, let me, just in case you guys missed what I said. Right, it doesn't have to be either one. It could kind of go like that, or it could go here. It doesn't have to be monotonic, right? That's what we're trying to show right now. What does monotonic mean?
Only decreases or only.
Or, yes, I love it. So what was true about a monotonic bounded sequence? It's bounded and it's monotonic. If it's bounded and it's monotonic,
It
what does
converges.
it do? It must converge because there's like a ceiling and a floor. So it's ready if it's decreasing or if it's increasing. It's got to converge. Does that make sense? If it's always increasing and there's a ceiling, well, that's like an asymptote. It's got to converge to that. That's exactly what a horizontal asymptote is. It's a bound on your function. So here, what's an plus 1?
3 minus 2 times n plus 1 e negative n plus 1.
Can you immediately see if that's bigger or smaller?
Did not help at all.
Isn't e to the negative n, so isn't this like dividing by e to the n plus 1? And isn't this multiplying by bigger and this is dividing by more? So I'm multiplying by bigger and dividing by more. So who wins? I don't freaking know. So I heard a magic word earlier about how to show something is decreasing. Derivative. Now what's wrong with this? Can I do a derivative of this?
No.
Hell no. So I gotta create the associated function. So what function is associated with this? Just make all the n's
3 minus 2x to
X.
the negative
right? Yes? So again, I really want this to make nothing but sense. Isn't this just specific points on the graph of this? So that lives in this. So whatever this does in the long term, this does in the long term because this lives on this. Now for discrete points, things like derivatives and integrals don't make sense. So that's why I have to look at its associated real input function. So what's this guy, and why would taking the derivative help me answer this question?
To see the rate of change.
Sure, and if it's what, it's what?
Negative.
If it's negative, it's decreasing. If it's positive, it's increasing. Okay, I like it. So what is f prime? I'll do the first part, that's 0. What do I have to do here?
Product rule.
Product rule. Derivative of x is 1. Plus, what's the derivative of e to the negative x?
Negative e to the
Good. Chain rule, yes? Chain rule? So see, that becomes a plus, so I get negative 2e to the negative x plus 2x e to the negative x. Now watch this. Can you guys factor that?
Yeah.
Yeah, you
What can you take out?
can e to the negative x.
And 2e to the negative x. So then I get x minus 1, yes? For any x greater than 1. What's true about this? Yeah, because what is this? This is always positive, yes? 2 over e to a power is positive. It's just getting tiny, but it's positive. And of course, once x is bigger than 1, so this whole thing is positive. What does that mean about this function? After n equals 1, what is this function doing?
Increasing.
Increasing. Now something I really want to make clear right now. It doesn't matter worth anything what this does for the first finite terms of itself. For the first finite terms of itself, it could be going down up until n equals 18 trillion, right? If forever after that it's going up, it's increasing. I can just cut all these off and say, okay, now it's there. Because how many terms are out here compared to back here? There's 18 trillion terms back here. What about this side?
Infinite.
It's an infinite number. Who gives a shit about 18 terms? Any finite number of elements doesn't matter worth shit because they're going up against, oh my God, Jeff. They're going up against an infinite number of things on the other side. This is going to show up quite a bit. Sorry. Got a little excited. Yes.
What if it oscillates forever?
Oh, well then, you know,
Neither.
that's not increasing or decreasing ever,
Okay.
right? Yeah.
So it's neither.
It's neither. Yeah. Okay. I like it.
But it can never be both.
Because, for example,
It can
real
never
quick,
constantly
what if I
increase
did this-
and constantly
What if I did
decrease.
this work and this was 105?
He said it can.
For the first 105 terms, it's decreasing, but afterwards it's increasing.
Forever after that, it's increasing. So fundamentally, it's an increasing sequence, an increasing series. Well, this is the sequence. I forget what section. Maybe.
But it wouldn't be monotonic, right?
Not officially, but
Okay.
again, I could pull off 105 terms, and then the remaining sequence is monotonic.
Okay,
You just
that's
have
I
to
just
start at 10 trillion.
Yeah, I mean that's what I mean. Like
There
if
you go.
n is starting at 1,
Yeah,
we have
if you look
800.
at the sequence itself in that case, if that was what we got, then the sequence is actually neither. But if I pull off the first 105 terms, the remaining sequence
Yeah.
For n at
is
106.
monotonic.
Yeah.
But like if we ever have a question, I don't think we will. But if we ever have a
Alright,
question
but
like that,
remember, the answer for a sequence, if this was true, this sequence would not be either. Because the sequence goes down and then it goes up, right? If I'm talking about a series, that gets more interesting, because now I can pull off any finite number, I can just pull it off, right? So let me show an example of what I'm saying. Is everybody cool with this? So derivatives are sometimes the way to go, and just comparing these are sometimes the way to go. Very often, if you just write this for yourself, you can go, I don't freaking know. All right, make that into an x, attack it with a derivative. Maybe. Okay. So what was I just thinking about? Let me think. Shit, I lost it. What were we just talking about?
A series that went down and then.
True. There's something else I just said. Damn it, Jeff. I'm gonna listen to myself. All right.
should we replay the tape?
Yeah, that would be nice. I'll figure it out for tomorrow. That's another reason why I make recordings. It helps me. For example, I'll look back at this again and remember what the quiz is supposed to be on. Okay.
Do you watch back all of these?
No, hell no.
That would be so much time.
This is all he does.
Study,
This is
it's
all
your-
he does with his free time.
Yeah.
It's not even
Or-
like you don't even have
Oh
enough
my
time in your
God.
life because he's like teaching most of the
That
day,
was
and
good.
then he has
Oh,
to
good.
watch
Did you really
recordings
go
for most of the day.
Do you have a
Alright.
coach that looks over your footage and is like, you could have done this right here?
You have a teaching coach?
Yeah.
A teaching coach. No.
Yeah.
No.
A teaching teacher?
I don't even. I
That's
told you
the
guys I
thing.
don't have a teaching credential either. You guys know that?
Well,
None of you-
most professors don't.
Almost none of your professors have. I was one class shy because I was going to teach high school. So I was one class shy of getting my high school certification.
Why
That was the
did-
one class that was 12 units big because I started going to grad school, started doing physics. So I just dropped
Decided I have better things to do with my life.
Yeah. Shoot. So- Oh, good. Here they are. So this is this. Does anybody else need 11.2 handout? The handout from 11.2? Oh.
I got it, I think.
Who else was it? You.
Me too. Know about his life?
Oh, yeah. If I'm sorry if somebody reminded me about this, but remind me again. I can put more of the handouts up on Canvas. I just forget. All right. Oh, okay. So we got a couple things to do. I'm not even sure if I'm going to make it to 11.3. That kind of sucks. Do I want to do that tonight? No, it's not enough time. So there's a while back I gave you section 11.1 handout
Yeah.
sequences, and on the other side was something called math induction. So we are gonna do that. We're gonna do that math induction. I just don't think I'm gonna do it tonight. So don't go scrounging for that. We'll do it next time. We don't have.
We got 30 minutes.
Probably. Well, I don't want to do it. No. It's one of my favorite things. So sort of want to do it. Let me think.
What is math induction? Are we inducting math?
You're
about
proving
math
things
conduction?
inductively. Yeah, let's do this. Why not?
Okay, so we are doing it.
One of my favorite things. So pull that out. The section 11 one handout. If you need some, I got extra copies.
Check this stuff.
I don't know where mine is.
Does everybody else have that?
Yes. 11-1?
Yeah, it's got sequences on one side and math induction on the other.
Yeah.
It's the one that has triangular numbers and then pentagonal and then Fibonacci. And then on the other side is math induction. Yes. Okay. So this is one of the coolest freaking. Okay. Math induction, the way this works is, for example, let's do the first example. Don't look at the thing, let's do it together. If I'm given, it's basically a way to prove a given claim about what an infinite sequence does. Bless you. It could also involve inequalities of a certain type, and I do have one example like that. Good. So the claim here is, if I add up, what kind of numbers are these? Odd numbers. If I add up all the odd numbers, and how do I write the most general odd number? 2n minus 1. It's 1 off from any given number. Bless you. Okay. So just to make sure, if n is 1, what do I get? 1. If n is 2, I get 3. Okay, good. So this is the nth term. If I add it all up to the nth term, the claim is I get n squared. Well, let's see. What's 1 plus 3?
4.
Is that something squared?
Yes. 2.
What's 4 plus 5? Is that something squared?
Yes.
What's 9 plus 7? Is that something squared?
Yeah.
Holy shit.
Pretty
There's
crazy.
a lot of cool stuff wrapped up in that, by the way. So we'll see in a minute. Let me see if I remember. So here, this is, all right. You'll start to see why I need to give enough time. The idea is, if this is a true statement, it needs to work at least once. You guys agree with me? I mean, if we already kind of proved it for several. So the first thing you do when you're given a statement like this is just make sure it makes sense. Get a base case. Not a basket case. That might be how some of us feel, but base case means for the first element, does it work? So in this case, it's kind of trivial. If n is 1, what do you get here?
1.
1. And is that equal to 1 squared?
Yes.
Check. Now, I relate this to dominoes in a sense. Okay. If I set up a bunch of dominoes, and they are close enough to each other, no matter which domino I click, it's going to fall over, and the rest of them are going to fall over. Is that right? So what I want to show, I want to prove that this domino, if I click it, it does make all the other ones fall. And if that's true for anywhere in the sequence of dominoes, what will happen if I hit the first domino? The whole thing falls, right? So this is all about assume this is true for some element in the sequence. And then show that that means that the next thing is true. So if I have a bunch of dominoes, right? I have a bunch of dominoes, seen from the side, and I say, let me start here. Let me show that it's true that if I push this over, they all fall, right? And if that's true no matter where I am in the sequence of dominoes, what's going to happen when I push the first one over? They're all going to fall. Amen. So again, right now you're all like, dominoes, what the shit? I don't. Okay. So watch this. This is one of my favorite things, which I don't know what that makes you feel when I say that. Assume it's true for some value of n. Let's say for n equal k. Everybody's favorite thing to do, right? Assume it's true for n equal to k. Let me make sure. Is that?
That's what it says.
Cool. Because there's a couple different ways to do this, and I prefer this way. But I think I base this on the way the book does it. So now, that means that we know this is true. Now this is the part that people don't like. When I'm going to show, if I assume it's true for one thing, no matter where I am in the sequence, I want to show that that means the next thing is true. The minute I've got that, don't I know the first guy's true? If I show that no matter where I am in the sequence, the next thing is true, and I know the first one's true, that means the second one is true. And if I know the second one's true, that means the third one's true, and all the dominoes fall. So I'm going to assume this is true, and this is where students have a lot of trouble. Like, how can I assume that? I really want this to make sense. If I, for the moment, assume this is true, and I show that that means the next piece is true, what does the next piece mean? K plus 1.
K plus 1 squared.
No, we'll get there. If it's true for the K plus 1th term, I'm golden. So let's just do that right now. So we know this is true. What does the K plus 1th term look like?
2k plus 2 minus 1.
It'll be 1 plus 3 plus 5 plus 2k minus 1 plus, you guys can do it, I know you can do it. If this is the kth term, yes, this is the kth term, what's the K plus 1th term look like? Is it going to go one more out? What do I replace K with?
K plus 1?
K plus 1.
2k plus 2 minus 1.
Yeah, 2k plus 2 minus 1, so 2k plus 1. Is that cool? Right, if we put a k plus 1 in there, don't I get 2k plus 2 minus 1? You guys see that? So if this is true, then if I add the next thing, it should also be true, yes? So what is this side supposed to be then? Just following this.
K plus 1 squared.
So here's the thing. I can't remember how I have it written down, but what does all this equal?
K squared.
We know it's k squared, correct? So I have to show that k squared plus this. We have to show that that equals this. Because that's what this shit's supposed to be, yes? If it follows this rule, when I add the next piece, it better equal this thing cranked up by 1, yes? So isn't all this shit, don't we know, we're assuming we know, that that is k squared. So k squared plus this better equal that. If it does, that means, yes it does, that means that if I know that any of them work, all of them work. Because if one of them works, the next one works. So sure enough, what do you get when you factor this?
K plus 1 squared.
You get freaking mad. And since this works, it works for the second thing, and it works for the third thing, and that means it works for the fourth thing, and that means it works for the fifth thing. So it works forever. Any value of it. Okay. Now let me show you something kind of cool based on this idea of squares being separated by all the odd numbers. Go with me for a minute. Let me see if I remember. It's been a while. Yeah, what's 12 squared?
144.
144, right? What's 13 squared?
169.
How
Nice.
far apart are these?
25.
What's 12 plus 13?
25.
All right, 14 squared. What's 13 plus 14?
27.
So if I add 27 to this, where do I get? 96, which is what 14 squared is.
That's math.
Pretty crazy, pretty crazy.
Right, isn't that cool? So that's the idea of the odd number separating, but when you add it to something really, really cool, meaning whatever these base numbers are, is what that should be. So then this plus this tells you what to add to this to get to what 14 squared is. So that's what, like those math human calculators, this is one little trick they know, so they kind of memorize certain places in the squares. Anyway, it's annoying. I don't want to do that. But that's what they do. Okay, let's try another one. Because that's the one that's worked out on the page. Yeah, look at number 3. Does that look familiar to anybody?
Not really.
Isn't that Riemann Sums?
Ooh, look at that. That we used in Riemann Sums. Which hopefully your teacher just didn't skip over. Riemann Sums, when you had to do the sum of I stuff. I don't know if you guys, hopefully you didn't just skip them over.
I don't even remember.
Okay, I understand. So this says this. What is it now? N plus 1, 2n minus, n plus 1, 2n plus 1. That's the one I always forget. This is where the sum of I was n times n plus 1 over 2. No? And the sum of I cubed was that squared, right? So you can use what we're doing now to kind of prove these. Be careful, what is I here? I is just the index.
Dice.
It's not complex. You guys with me? I is just the index. I don't know why I put, wait, is it just to n? Right, yes, just to n. That's where you're going crazy, Jeff. Don't want to go to infinity. Okay, that's better. Okay, because then the next thing you did was let n go to infinity, and that's where the big ass S symbol came from, right? Okay, maybe. Is that coming back a little bit? Infinite rectangles, infinite resolution. Okay. So I need to write some of these terms out so I can make it look like what we just did. So this will be 1 plus.
Are you waiting for us?
Yeah.
Oh.
4 plus
9.
9
16.
plus I squared equals, plus n squared, sorry. Because the last thing I plug in is n, correct? Equals n times n plus 1 times 2n plus 1 over 6. So what's the first step? Base case. Does it work for n equal 1? If n equals 1, what's this side?
1 times 2 times 3 over 6.
If n equals 1, it's going from 1 to 1. N equals 1, what's this? So how far do I go? 1. Does that equal 1 times 2 times 3 over 6?
Yes.
Yes, does everybody see where I got that, right? Just
Yeah.
plug a 1 in for n, yes? Check, base case works. So if I can show that something being true means the next thing is true, and combine it with this, it's always true. To me, when I first learned this, I was like, what shit? What? Holy shit. It was just so cool. And some of you guys, I'm sure you may be saying that same thing, but maybe not for the same reason, but I don't know. Yes?
And to clarify, you can let n equal any number, right? As long as the base case is true.
Yeah, as long as the base case is true, you could let it equal any number.
0.
You gotta be a little careful because the proof is assume one thing is true, does that mean the next thing is true? So it doesn't kind of work backwards necessarily. So you gotta be a little careful with
So
that.
is it usually good to start just right at the beginning?
Always start right at the
Just
beginning.
keep it simple?
Yeah. Keep it simple. So,
Why not start at 0? Wouldn't that make
Could not natural number.
okay. What's the next step? This is the step students don't understand why we can do it. Assume what?
It's true. It's true.
Assume it's true for what? And this is the step that either doesn't make sense or students are like, why the shit do you make it? I don't know what n is. Why do you make it k? Well, n is just anything. K is a specific place. So on one level I know we're just trading variables, but it's a very specific reason we have to do that for a specific value of n. Let's call that k. We're assuming it's true for that. So what would this be? 1 plus 4 plus 9 plus
K squared.
k squared equals k times k plus 1 times 2k plus 1 over 6. Okay. So what would n equal k plus 1 look like? 1 plus 4 plus 9 plus k squared plus k plus 1 squared. And that's supposed to equal what? You're in the k plus 1 term, what happens here? K plus 1
Times K plus 2.
k plus 2.
Times
2k plus 2 plus 1, 2k plus 3. Is that cool? All over 6. I don't think I did it quite like this on the thing, but I kind of like this method here. I think I had trouble figuring out how to do this. What is this assumed to be? What do we assume this up through k squared to be?
K times K plus one.
Yeah, that physics. K times k plus 1 times 2k plus 1 over 6 plus k plus 1 squared. Oh my god, red dude. Poor little red dude. Other red dude. Let's see.
Oh, that's a horrible sound.
What's got to be? Ooh, hello. I'm sorry. What does that have to? We don't want this to make all the sense in the world. Okay. I know this is weird. You're not used to doing this. This is a weird little proof. You're not used to proofs. We're assuming it's true for k. No matter what k plus 1 would mean has to be true. And this means, since that is this is that, when I add this, I better freaking get that. That would mean it's true. So much writing. Oh, okay. So what the shit, what do I do here?
You just give it the same denominator.
The same denominator? Oh my gosh, we need more room.
Yeah, me too.
All right, mascot. What I would do.
Are you the mascot?
We should buy
Is
you a
this
funny
cool?
costume.
It just needs a 6, right? Is that cool?
Wait.
He just needs a 6. Bam,
Just
bam.
multiply by 6.
Yeah.
Now, please, dear God, don't multiply all this shit out. What can you do? What can you do? What can you do? What can you do with this? Good sailor.
It's 7.
What do you want to have happen here? What do you want to have right there?
Factor it out.
Don't you want a k plus 1 right there?
Yeah.
Yeah, look. Let's take a k plus 1. There it is, Jeff.
Alright.
Can you take a k plus 1 out? So if I take a k plus 1 out, I'm left with 2k squared plus k plus 6k plus 6. Is anybody not cool with that? If I take a k plus 1 out, this is 6k plus 6, right? Because I lost a k plus 1. Here I lost a k plus 1, so it's 2k squared plus k.
And that factors.
There's k plus 1, 2k squared plus 7k plus 6, become a k. And now I bet you anything, over 6. And watch, since I know the answer, look, 2k squared plus 4 plus 3 plus 7k plus 6, that's exactly how this factors, yes? It's awesome to know the answer, you just have to verify, hey, that is that. And what was it? Okay, k plus 2 times 2k plus 3, all over 6. So since this leads to this being true, because we just showed it, knowing one thing is true means the next thing is true, and we know the first thing is true because we did the base case. If the first thing is true, then the second thing must be true. If the second thing is true, then the third thing must be true, because we showed if one thing is true, the next thing is true. That's what this means. Really, do you guys see that? If I assume this is true, and we just showed that leads to it being true for the next thing, all I need is the very first thing to work. Because that means the second thing works, which means the third thing's working. Dominoes falling forever. Yes?
I'm confused how you got those functions on the left there.
This?
Yeah, I don't know how you got.
Right here. I just took this and put it there. That's all I did. So this equals this from here, right? This equals this plus this, right?
Did you distribute them out after that?
From here to here.
Yeah.
I took a k plus 1 out.
Right.
So that's 2k squared plus k plus 6k plus 6. Because I took a k plus 1 out, right?
Oh.
So of course there's no k plus 1 there, so that's 2k squared plus k. There's 1 less k plus 1, so that's 6k plus 6. Kabam. Yes?
What's like the point of this stuff?
That's the real question.
Good question.
Now we know this is true. We just proved that's true. And what could you not do without that knowledge? You could not have integrals. Some of you guys might be like, what's so wrong with that, Jeff? And then I could do the standard math stupid thing to say, well, then you wouldn't have a smartphone and you wouldn't have a computer. Which is not really far from the truth. I mean, you don't even know how much integration does. Almost every software package has an integral subroutine somewhere. Well, trust me. Anybody doing computer programming? A huge part of computer programming, when you get far enough along, is to figure out what is the best integration subroutine I want to use. What's the fastest one? What's the best one? And you can use a different one in different situations. Here you want a fast one. Here you want a more accurate one. Here you have something that's got more tolerance, right? So you have a different, maybe. Anybody bowl at all?
Yeah.
You bowl? Do you have balls for different lane conditions? Bowling balls for different lane conditions?
No, I'm not a professional, but I do.
My
I
little
keep my
brother
bowling
did.
ball in my
little
car.
brother
all the
made
time.
money in tournaments, and he had a different bowling ball for every lane condition. He had like 12 different bowling. He'd go to the lane, he kind of, yeah, oh yeah, I need this one, and then he makes the money. I'm like, whatever.
Well, most.
Anyway.
Yeah.
So anyway, I forgot what my point with that was.
Yeah. Wait. What was the? How did the bowling?
Um,
You need a different subroutine for different
Yes.
conditions.
Different subroutine for different conditions, thank you. So if you get far enough along in computer programming, especially if you do something more STEM related with it, because believe it or not, computer programming can go in multiple different directions. You're gonna be interested in subroutines that involve integration. It's just the fact, right? So you want to be able to program something like this in your subroutines for integration. When you do integration in your calculator, does it actually, what does it do? Does it actually find the antiderivative? No, not necessarily. No, it doesn't. It does something akin to Riemann sums. In which case I need this programmed in my freaking calculator. So if we didn't have this, there's a lot of shit we wouldn't have, right? I'm sorry. So yeah, that's, it's a little important. Okay. No, you stay there. All right. Last thing for today. All right, this is a lot here. So if you want to, you can try out this other two on there. I can't remember where this shows up in the homework.
It shows up in the homework?
I thought it did, but maybe it doesn't.
Is it going to show up on that quiz next week?
It'll show up on the test for sure, in the bonus. Last thing for today. And this is the integral test. So just to give us a little, we kind of looked at this already to a certain degree. So if I have a sequence that is decreasing, so given an, a decreasing sequence where an greater than 0, so all the terms are positive, then if the integral from 1 to infinity of f of x, where f of x is related to an, you guys with me? If that converges, so does an. Now here's a beautiful example of what I was trying to say earlier. If I have a sequence, and this is where this comes into play. If I have a, so does the sum, so does the series. Be really careful with that, sorry. So does the series. So and again, it kind of makes sense because what does this symbol represent?
The area under the curve.
Sum.
What kind of sum?
Sum of a.
What is going
Sum
on?
of a gun.
Infinite sum, right?
Yeah.
It's an infinite sum. Limit as n goes infinity. A sum of infinite rectangles. Alright. If that freaking converges, then the thing who only uses certain elements of this and adds them up will converge. I want this to make all the sense in the world. So if an is 1 over n squared, Jeff. If an is 1 over n squared, Give me some elements. What's the first element? 1. Holy crap. Let me put it up here. What's the second element?
1/4.
1/4. I love it. What's the third element? 1/9. Fourth element? 1/16. All right. So when I add those, I'm adding up those specific function values, yes? So if the associated f of x, in this case, what would f of x be? Just 1 over x squared. What does it look like?
The same thing.
No. It includes
It's
everything else. So if this area converges, right? If adding up the infinite number of things in between every element of this converges, then so does just doing this one and this one, right? I really want that to make sense. The integral adds up everything in between those points, whereas this just adds up the points, right? So if this dude converges, shit, yeah, this one converges. Now this doesn't tell you what it converges to, it's just a test for convergence. It just shows you if it converges. So if this integral diverges, so does that. So it works both ways. So if it converges, so does the series. If it diverges, so does the series. So let's look at one example. I think you guys know what I'm going to do, maybe. What did I say earlier I want to show you better proof of?
the harmonic.
Aromatic series, right? So let's take a look. I'm going to erase this. No? First I'll give you this. It's got the rule on here, too. So you got it written down for yourself. Just as disappointed as you are that I haven't let us out here yet. You're like, you're the teacher, man.
Some of the if-then statements, they don't always work both directions.
In this case, it's explicitly stated it works both ways. Pretty sharp with that.
Very cute of it.
Yeah, okay. I said it better on there. I like it. So, let's look at 1 over n. So if I want to use the integral test on it, what am I going to integrate?
1 over x. So f of x.
All right, so let me do this better. So the integral test, 1 to infinity, 1 over x dx, and of course that's freaking nice. What do I have to do first though? Somebody else said it earlier.
You don't know that.
I have an improper integral, right? Okay, we'll do. So what is that integral, of course? Natural log of x.
X.
Why don't, I don't need to ask that because it's all on that. Sorry. Natural log of x from 1 to t. Limit as t goes to infinity. Natural log of t minus natural log of 1. What's the natural log of 1? 0.
Oh.
So what happens to this as t goes to infinity?
It's big very slowly.
But still, it goes to infinity.
Diverges.
This integral diverges, therefore, this diverges. Much better, yes.
Do we have to prove it's decreasing?
Oh, yes, you do. But this one's
So,
known to be decreasing.
1
So
over-
1 over n is exactly what we just had up here, basically. So it's 1 over squared. 1 over n's like that, right? How would you show very quickly this is decreasing? You have 2 ways you can do it.
You show that n plus 1 is less than.
Yeah, so an is 1 over n. What's an plus 1?
1
1 over n plus 1. This is divided by bigger, so it's getting smaller. Or you could even take its derivative, which is easy. What's the derivative of 1 over x?
Negative x.
Negative 1 over
X squared.
X squared.
x squared is always positive, therefore this thing is always negative, so it's always decreasing. So do you see how both ways could show you it's decreasing? You either directly show the next thing is always bigger, or smaller, sorry, or you show this, the derivative is always negative.
So 1 over n squared would be convergent then.
Convergent, yes, because when you integrate 1 over x squared,
You get negative 1 over x.
which goes to
converges to
0 when t goes when x goes to infinity.
Boom. Okay.
Beautiful.
That's a good test. I like that test.
So
a
the
lot
next thing
more.
we got to talk about, we're not going to talk about tonight, is something called p-series. So if anybody's been reading ahead, we're going to finally get there.
Can we use the integral test on 11 too?
Second,
Are the limits always 1 to 3?
it depends on this.
I know, but
This
I
could
want to
be
see.
3.
I want to double.
It's always infinity, but this could be 3 or 4.
P
or
series
7,
is the best one. It's my favorite
or
one.
0.
Which one?
P series, the one we're doing next.
Okay.
Sorry.
Can I use you're good. Can I use integral test on 11 too?
No.
No.
Because we learn it in 11.3.
Okay.
Okay.
I'll live. Thank you.
Could you grab my phone real quick? Thanks, Rob. I got you.